Before we start with Victor's talk, I also like to make my quick announcement. For those of you who haven't seen me last week, my name is Carsten. I work for G-Data, Advanced Analytics, and we are supporting this course with an additional evening event, which will take place today and also next week when Mario is our speaker. So what's the offer? We are going to have a nice dinner at our rooms and also have some good drinks and a cozy atmosphere for hopefully nice technical discussions and everything. Victor will join us later, but unfortunately he will not stay long because he has to go back home. So yeah, if you would like to take the opportunity to talk to him a little bit more in detail later or get in touch with people working in the technical field from the antivirus industry, all of you are welcome to join us and feel free to ask me after the talk. And besides all of that, G-Data is always looking for new people. We are hiring in different fields, offering thesis works or practical experience or whatever you need. So if you're at a point at your studies where this could be interesting for you, don't hesitate to ask me after the talk. So this is enough from my side. Please welcome Victor.
Yes, hello, thank you for the introduction. We're also looking for people, actually. So if you're finishing your master's, or if you're doing a bachelor and you want to do a master abroad, then you can come to VU in Amsterdam, where I'm from. So my name is Victor. You can follow me on Twitter. I'm a PhD candidate at Vrije Universiteit in Amsterdam. And today I will talk about Drammer, which is the Rowhammer on mobile phones, but more particularly I will talk about the making of. So it will be a story a little bit about research, also how we did research on this topic. So Drammer is this new attack, or well, published last year at CCS, that allows you to root your Android phones with Rowhammer. I will talk about Rowhammer in a minute, but basically we can flip bits in memory and we can use this to do nasty things to your phone. Now, I gave this talk at Hack in the Box, which is a hacker venue in Amsterdam. And the question there, actually, what we got is, why should we care about a making of? Right? So, of course, the work itself, Drammer, is very interesting, but yeah, the making of, what does this give us? So I wrote down a few points. During this talk, you will get some insight in the academic thought process. So how did we came to the conclusion of doing Drammer? How structured did we work on this? I'm going to show you some interesting new techniques to do Rowhammer. I'm going to talk a little bit about, hey, there you guys are. These are my colleagues, some of them. Can you raise your hands, please? Yeah. I'm going to talk about some negative results and mention that negative results are also results and could help other people in doing research so that they don't follow the same path that I did. And I will also show that it's fun to talk about a making of. A disclaimer I added is that this will be a technical presentation, but I think you're all equipped with some technical background knowledge, so that should be fine. The presentation will be about me, so I added this for Hack in the Box because you have multiple tracks there, and I said, if you don't like me, then you can now move to another track, but you have only one track, so you're all stuck with me. And there will be some strong language in the presentation, so don't be offended. So who am I? A little background. I'm a PhD candidate at VUSec, which is our network and computer system and network security group in Amsterdam. We have a very cool website, WordPress. Check it out. We have all our projects there. We have nice videos of what we do. This is a picture of our group. And so the guy in the middle there, he's sitting over there. This guy, that's Herbert Bos. He's the professor of our group. Then there are other smart people as well. I have a pointer. So there's this guy, it's Cristiano He's an assistant professor, and there's also this guy here. He's sitting next to Herbert. He's a postdoc. He was very involved in the Drammer making of. Also, who else is important? So this is me, of course, and there's Ben. He will also show up. And the other people are postdocs and PhD students, a mix of those. So I'm doing a project, or I'm being paid to do a project, on dynamic analysis of Android malware. And this project is funded by the Dutch-American cooperative Vrije project. And it's basically in collaboration with the University of Santa Barbara in California. So it's about Android malware. And I started in June 2014. So I previously did some work on dynamic analysis of Android malware. I built this framework called TraceDroid. I worked on Anubis a little bit. And then I started my PhD with Herbert to continue working on this. Now, for this presentation, there are some important dates that I will be talking about. Starting with February 18 in 2016, which was the deadline for using security. So one of the conferences we tried to submit our papers to. There was, 6 days later, there was Financial Crypto, which is a second-tier conference, I think. It was in Barbados, and I had a paper there about Bandroid, which is another Android attack. Then on May 21, there was Security and Privacy in Santa Barbara, where we had the Type Armor paper with some of the guys here also from Bochum. And then 2 days later, there was a deadline for CCS. And then the idea was to, for me to go to Santa Barbara and to live there for 3 months between March and May and do a project about Android malware with the guys from Santa Barbara. Okay, so let's start with the beginning. Before February 18, I was working with another guy from our group, Dennis, on a paper about disassemblers. And we were basically trying to figure out how good the disassemblers these days are. We wrote a paper about it, submitted to Usenex. Was quite some stress to get it all done, of course, before the deadline. I had to take care of a hotel because I was going to Barbados to present my work there. I also had to take care of a flight, figure out how to get to Barbados and then to Santa Barbara. And I also had to find a house. And the interesting thing here is that I was not by myself, but I was also bringing my girlfriend and our daughter to Santa Barbara. Also, during this period, I was in Cave, sitting there, and Ben, from the picture, working on their paper, which ultimately got published at Usenex, called Flip Feng Shui. And I think something Rowhammer in a needle haystack, whatever. Basically, I was watching Ben and Kave breaking the internet. And what they do with their work, I will discuss it later in detail. They do cross-VM exploitation, so they break from one VM into another VM using Rowhammer and memory deduplication. Now, a little bit about Rowhammer. Who here is familiar with Rowhammer? Some people. So who had never heard of Rowhammer? Okay, nobody. So that's good. I will briefly go over what Rowhammer is, how it works. So Rowhammer is a glitch in your DRAM. It's a hardware issue. And if you look closely at DRAM, then basically you're looking at memory cells, so-called capacitors, that store a charge. And a charge can represent a 1 or a 0. These so-called capacitors, they have a natural discharge rate. And what this means is that when you store a charge inside the cell, over time, the charge will leak and your stored bit, 1 or 0, will disappear. This is why your DRAM needs to be refreshed every 64 milliseconds. So DRAM has a refresh rate, normally every 64 milliseconds. And in this during this refresh, the memory controller will recharge, essentially, the capacitor. Now, people found, not we, but other people found that if you access cells very frequently, reading from them, you can increase the rate at which neighboring cells that are close by, the cells that you're accessing, you can increase their discharge rate. Now, you can do this to do Rowhammer. And Rowhammer here, you have a victim cell that you store a 1 in, and a high charge. Then you access cells that are very close by, very frequently, and then this victim cell with the high charge stored, it will leak its charge faster than it should be, and then when you read it, actually the 1 will be gone and it will be a 0. So you end up with this disturbance error, and basically you're flipping bits in your memory. Now I have a picture of this. This is a single-sided Rowhammer, a very simple example. Imagine your DRAM is this matrix of 1s and 0s, small cells. And so it's a bit hard to see, but I'm now accessing the second row, and then I'm reading something else. Then I'm accessing the second row again, and I'm continuing to do this, and then you will see that in a cell next to this row that I'm reading from, the charge is leaking and leaking until at some point the 1 that was stored there turns into a 0. Some terminology. The row that we're reading from is called the aggressor row. The row in which we flip a bit is a victim row. It's important to know that with Rowhammer, not every bit may flip. Also, sometimes not every DRAM module may actually be vulnerable to Rowhammer. But we find that once we flip a bit using Rowhammer, we can often reproduce it. So when we know that this particular cell is vulnerable, we can then try to store some important data in there so that we flip a bit another time, something interesting happens. Then people found out that, hey, we have single-sided Rowhammer, but we can also sandwich the victim row with 2 aggressor rows, so reading from these in an alternating fashion. And by doing this, you can actually increase the chances of flipping a bit drastically. Unfortunately, doing double-sided Rowhammer from an attacker perspective is a bit harder to pull off, so there are some more requirements. So what are the challenges for an attacker? Let's say you want to flip bits in your memory. Basically, there are 2, or at least 2 that I will talk about during this presentation. One is that you need to bypass the CPU cache. And some of you may know that normally when you access your memory, the data that you access will be then stored into the cache of your CPU. So the next time you're going to access this address, this memory, the CPU will actually read it from the cache, and it will not propagate it to the DRAM. If you want to do this double-sided Rowhammer, then you need to know, you need a way to figure out from which addresses in memory you should read from, so that you're sandwiching the victim row correctly. And how do we know what these addresses are? So zooming in a little bit on this, bypassing the CPU cache. So DRAM accesses are slow, so these DRAM, these capacitors, they're really slow, but you can use them to store a lot of data, so they're pretty useful. But normally when you access once one of these rows, the data will be stored in the cache. So that next time the CPU wants to access the same row again, it will read it from the cache, which is much, much faster. However, if we want a Rowhammer, we want to read from the cache, from the DRAM many, many times. So we don't want this data to be cached, so we need to bypass the CPU cache. One solution that we have seen so far is using Gasflush. And this is basically an instruction where you tell the CPU, please remove this bit of data from the CPU cache so that next time I read it from DRAM. Another solution is using cache eviction. So you can read more data from DRAM until you fill the entire cache or part of the cache, and then your aggressor row will be removed from it so that you can read it again from DRAM. The second challenge, selecting the aggressor rows. For this, we should know that DRAM works with physical addresses, illustrated here with an example, but your software usually works with virtual addresses. So you can allocate a buffer in C, and you get this list of virtual addresses representing your data. And then you have physical memory on the right side. And then the problem here is that this mapping from virtual addresses to physical can be random. So there is an unpredictable mapping, and the question then is, how do we know that we need to read from these two addresses to get two aggressor rows in our DRAM? Well, one solution is don't, and then you end up with doing single-sided Rowhammer. You just read from two addresses, and you should be good. But there will be less interference, and there will be less bit flips. If your DRAM is bad enough, this will still work. Another solution that people have been using was the page map, which is a special file on Linux that holds this mapping. So you can basically open this file, and then you can look up this address, virtual address here, and then it will tell you the physical address. Another solution is huge pages. And these are virtual allocations that are mapped to a physically contiguous region of memory. So then you end up with a buffer with virtual addresses that are not the same as the physical addresses, but we know that once this first virtual address maps to a certain address in physical RAM, all the following virtual addresses will also map to following addresses in the physical memory space. So with this, we can do Rowhammer exploitation. And if we want to do Rowhammer exploitation, we need to do two things. Three, actually, sorry. One is memory templating. And this is a phase where we search the entire DRAM area for bits that we can flip. Once we have that, once we know that a certain cell is vulnerable, we want to land some sensitive data into that cell. So we need to store something into that location. Once we have that, we are going to reproduce the bit flip and hopefully do something interesting. This mechanism, these three steps, is what we call flip feng shui, and which was written by KV and Ben, published at Usenix. Okay, so going back to before February, or mid-February, I was watching KV and Ben breaking the internet. Here they are, giving a talk about this at Black Hat in Europe. The paper was titled Hammering a Needle in the Software Stack. And they have a malicious VM in the cloud that is going to compromise neighboring VMs. They're going to use Rowhammer, what is described, and memory deduplication, and use this to flip a bit in another VM. Now the question is that you need to think about a little bit. If you are in a VM and you can flip another bit in another VM, what would be an interesting target to flip? Meanwhile, I will talk about memory templating. The threat model of flip feng shui is that victim and the attacker are sharing the same hardware. So in this illustration, we have two VMs on one machine running with that share the same hardware, including DRAM. The attacker has all the privileges he wants on the VM, so he can use Gasflush to bypass the CPU and to Rowhammer, and then he can use huge pages to get contiguous memory allocations and to efficiently do double-sided Rowhammer. So that's what he is doing, right? First step is templating, is going to allocate some memory, and then it's going to write some zeros and ones to it, read from it many times, until at some point here he will find a bit flip, a 1 to 0 bit flip. Then the second step of this feng shui is landing some sensitive data. So given a bit flip in the attacker VM, how do we force the victim to store something in this location? For this, they use memory deduplication. So what is memory deduplication? It's pretty straightforward. You have memory, you have physical memory here. Here's the bit flip. And we want to store something at this location. Now let's look at an attacker having a buffer allocated which stores some data, and then we have a victim that has a different buffer that stores also some data. Memory deduplication means that the operating system is going to actively search memory for duplicated pages. So it will find that the victim has some data stored in a page that is actually exactly the same as a page from the attacker. Now, what happens next is to save some memory, is that the victim's mapping is updated, his original page is removed, and now the same virtual address is pointing to a different physical address, exactly the same that is used by the attacker. And why would you do this? Well, you do this if you're a cloud provider, so that you can save memory and you can store more VMs on the same hardware, so you can make more money. But in Flip Feng Shui, we can use this to force the victim to store something into that memory region. Now coming back to the question, what should we flip? Does anyone has a suggestion on what we can flip if we have this primitive? Is it going to be no one? We have to ask Gabi. You have
probably some hypervisor flags also.
Hypervisor flags? Will it work? Maybe? Maybe? Anything else? So I remember that it took some time, I think, if I recall, to come up with something. Basically, the question is, what should we land here, right? And then they ended up with this very smart insight that you can land a cryptographic key in this region and then flip a bit in a key. You can also store domain names in a vulnerable region and then flip a bit in a domain name. So let's look at what they did in the paper. Are you all familiar with SSH? Most of you? They're going to store your public RSA key that you can get from authorized keys into the page that is vulnerable for Rowhammer bit flips. Then they flip a bit, and basically what they're doing here is they're changing the cryptographic key in such a way that it loses the important properties of RSA. So after flipping a single bit, all of a sudden this large number, which is a multiplication of two prime numbers, which should be very hard to factorize, is now suddenly very easy to factorize. So after they flip a bit, the attacker can compute a new private key matching this corrupted public key, and then use this new private key to get SSH access to the victim. Okay, I'm gonna drink a little bit. Now this is cool. I thought it was nice. But of course you need to know the public key of the victim that you're attacking. So they also came up with another attack, which is zero knowledge. They're going to flip a bit, not only in cryptographic keys, but also in domain names. So what happens if you're doing an apt-get upgrade on your Ubuntu VM? You will actually go to a domain, security.ubuntu.com, and then ask the domain, are there any packages that I should install? Is there anything new? Now, if you flip a bit in this domain name, so that ubuntu.com becomes ubuntu.com, and if you then register this domain name, ubuntu.com, then the victim will no longer ask ubuntu.com what's new, but it will ask the attacker what's new. So what the attacker now does at ubuntu.com, he will host a malicious core utils or ls command that the victim will then have to accept as an upgrade. Of course, things were not easy, not this simple, because packages are also signed. So they had to flip another bit in the GPG keychain, so they had to find another vulnerable location, store there the GPG keychain, flip a bit there, and then compute a new key that matches this and sign the packets that he's hosting online. And then you simply wait for the attacker to do an upgrade, which usually happens automated. Okay, so after the paper got out, these guys contacted NCSC. Which is the Dutch Cybersecurity Center. They did a very good job of contacting all the parties that were affected. There was a GPG patch fixing it so that self-signed keys are no longer valid, so this attack no longer works. And also we bought some of these domains for Ubuntu and Debian that are one bit flip away. I always used to say when I'm giving this talk that if you think you're the appropriate guy that has access to this domain, you should contact us. Kave, do we still have these domains? Or? Okay.
I asked them to also register. I don't know what they did.
Okay.
Last communication was, I think, 3 months ago.
Okay. So maybe if you're lucky as an attacker and you want to do this. Anyway, afterwards, Ben and Kave were happy that they submitted the paper to Usenex and it ultimately got accepted. Okay, so part 2. Drammer. I was following these developments of Kave and Ben working on this, and every day I got to the VU, they came up with a new part of the attack, right? So every day I was watching them in their office, and after 1 hour I was like, no, I'm going home, I'm going to disconnect everything from the internet and I'm going to do something else. But also it got me thinking. So on this date, I was chatting with Kave, and then I asked Kave, can you do Rowhammer on Android? Stupid question. Kave's response was, yeah, it depends on the speed of the memory controller. We should do some testing. Okay. So I did some Googling, as you normally start your research, right? Maybe somebody else has done this already. And actually, I found this tweet in March 2015, which was briefly after the original Rowhammer paper was published, and where this guy is asking about whether or not ARM has something like seal flush. So is there something to explicitly flush data from the CPU? He got responses from Alex and from Half Flake saying, yeah, there is such thing, but ARM is not stupid, so you cannot really use this from Userspace. Also, same as Kave said, Halvar said, responded that it's not sure whether the memory controller on ARM is fast enough to trigger Rowhammer bit flips. We also I also found this other material. And it was a report, an issue on Chromium, also about Rowhammer, whether or not there are other instructions than seal flush that should be considered harmful. So they say that it might be a good idea to look at other instructions that might allow you to flush the CPU cache to make sure that you cannot do Rowhammer on ARM. Good. Anyway, I couldn't find any reports of bit flips on mobile devices. So around the Uselinks deadline, I wrote this email to Yannick and Martina. They are in Santa Barbara, Userspace people. I was saying, yeah, some people at KB Bend are doing this awesome Rowhammer stuff, and it got me thinking, can we do this on Android or iPhone devices? And I mentioned this. I know that the original plan was doing this project on dynamic analysis of Android malware, but maybe we should look at Rowhammer, because it might be worth investigating. So I got a reply a couple of days later from Yannick. I have no idea why people are not looking into this, so yeah, sure, let's do it. Good. But first there was the trip to Financial Crypto, to Barbados. We have to present there. I can recommend everybody to submit your paper to Financial Crypto. It was really cool. Then we arrived in Santa Barbara. This is the right side is our house with of course, there was an American flag hanging out there. And then March 1 to March 18 was basically me bootstrapping, getting ready into research mode. And I have there on the right side, you see the paper deadline for CCS. So we were aiming CCS. We wanted to do something with Rowhammer on mobile, and the goal was ideally a CCS submission. So bootstrapping, of course, I had a SMP paper, very happy about it. Type armor, we do some control flow integrity, CFI. But there was a deadline for this, because when you submit a paper and it gets accepted, you have to make it look nice, polish it. This took me some time, submitted after the deadline, of course. But it got published, and also it's open source now. Anyway, took me some time. Meanwhile, I did do some work, because on March 10, I tried to boot a custom kernel on Android. So I never played with this before, but I took out one of the Nexus devices that they had at the lab in Santa Barbara and tried to compile my own kernel, because I knew already that we cannot flush the cache explicitly from Userspace. So let's try to do it from a kernel first to see whether we can even flip a bit. So there was kernel version compiled at my own machine. So March 10 we had a phone that had support for loading kernel modules. And then the idea was to write a kernel module to Rowhammer the memory. Sorry. Okay. March 11 is about measuring the speed of your DRAM. So Kave was saying on chat, we usually use Hangouts, he was asking me, can you run stream? I'm curious. And then I said, stream? What is stream? Never heard of it. So he pointed me to this website, and then I found that stream is a benchmark, a simple synthetic benchmark program that measures sustainable memory bandwidth. Okay, cool. It's an ARM binary. Let me try to compile it. And I sent him this. I had absolutely no idea what this means. But there were some numbers, and no, it was not good, according to Gave. 2 gigabytes per second might be enough, but it's not ideal. Still should maybe work. And then he was saying, I'm not even sure how he got these numbers out of it, but 2 million operations per second is ideal, and right now it's 0.5 million. Good. That was very comforting, very promising to continue working on this. So in March 11, we did stream, and then March 18, the security and privacy deadline. And then after that, I started working on the kernel module, just trying to write code to Rowhammer. And on March 23, I succeeded, or sort of succeeded. So I wrote this small ARM assembly function that was working with my kernel module. And it could be used to hammer through addresses. So I can quickly go over it, because it's not very hard. These are just variables. These are the two addresses that I'm going to read from. So the two aggressor rows. So loop, and then you read it. One address, you read another address, and then these instructions are used to flush these addresses from the cache. And then you subtract a number from the loop, counter, and then you loop. And then I said, tomorrow, KW, I will look at porting meh.cc. So what is meh.cc? It's a piece of art. Actually, it was more like a resurrected piece of crap from the remainders of Flip Feng Shui. It was based on Rowhammer.js, which was then based on Project Zero code. So many people touched it. And then my job was to port it to Android so that it would use my kernel module for hammering. KW was saying that there was a meeting in 6 hours. And then I was saying, sure, if you have a meeting in 6 hours, then you have still 6 hours to port your code to ARM. So he said, yeah, maybe you can show me an example of how I can communicate with your kernel module. So I explained him how this was working. And I made him do a promise that when I wake up, it was the middle of the night for me, there should be bit flips. No doubt, but we can at least try. And then he was showing some output saying, yeah, I'm hammering rows, and then I got 256 and 257, but this is 0, and this is a weird number, must be wrong. You can go to sleep, I will fix it. Okay. Later on, you got a return value 0. What does it mean? And I was saying, yeah, it's the number of cycles it took for the hammering to take place. It's not good. Yeah, sometimes it returns 0 because I'm a very good researcher and I can write no code at all. Well, sometimes it returns a larger value. And then I realized that the thing that we were doing was actually quite scary in a sense, because maybe we find no bit flips because we cannot write proper code. Or maybe we were unlucky with our hardware. So maybe we were looking at a phone that was not vulnerable while the next phone in line was. Or maybe the controller was too slow. So basically there were too many scenarios that could go wrong. Closing my laptop, let me know how it works. I started looking into this bug, and then concluded that this is very weird. Because this instruction here, this set of instructions here is writing 98, but the MCR instruction that I was using, so in this one, it should get the cycle count into R3, which is here. And it wasn't doing that. What is this? Maybe KW knows why he didn't. And then I found out what was really going on. So you have this instruction on ARM. I'm not sure, maybe people are familiar. There's instruction MCR that does some stuff with a coprocessor, so-called coprocessor. But you also have another instruction, and that also does something with your coprocessor. And this instruction is MRC. See the difference? So, and the difference was one is reading, and the other one is writing. Yeah, and then ARM said, I thought the ARM's instruction was supposed to be nice What's nice in an x86? Anyway, I should sleep. I'll look at this later. And I managed to get mad.cc in a workable state, and I just turned it on to hammer with one of these phones I had, but I was already pretty pessimistic about this going to work. We probably won't see anything. Kave is a very positive person. Tomorrow we will find bit flips. Just let it run overnight, and tomorrow we will have something. Okay, so the next day was basically debugging, code, hammering again, debugging, etc. So it was at 4 in the afternoon, no flips. A couple of hours later, still warning, no flips. I don't trust that this is going to work. 4 hours later again, still no bit flips. Kave was still positive. Just wait. Also, if it would have been easy, then people would have been reporting bit flips already. That's true. And then I got an email the day after from the boss, Herbert Bos. There was an email list conversation going on, and then Herbert said, I'm going to add Victor to this list. So he's, as mentioned before, he's at Santa Barbara, desperately trying to flip bits on ARM, and he's not allowed to go surfing until he gets a bit flip. That was on March 25. So, March 26, flipping bits on the beach. I woke up, and I was saying, Kave, this can be wrong. This must be wrong. So I was seeing this, found one bit flip, and then this should be the original value, and this should be the new value. And then it means that all the bits in a single byte were flipped in row 254, and this should be something else. When hammering, and then here's nil, and then a long index. That must be wrong. Kave agreed, that doesn't look like a bit flip. But could be that the code that's actually printing the statement is wrong on ARM. And then I was pasting some more of these output. And then, I concluded, it's weird. It's in row 254, but it just said that it was hammering these rows. So what do you think? Maybe some people see it already. So there's 254 here, which is FE, which is exactly one bit flip away from FF. Kave was busy. So we didn't spot it at the time. Looking into it, it's weird, probably casting issue. Some little big Indian 64-bit code, blah, blah. I really didn't care. I just wanted to know, is this a bit flip or not, or likely? We have to test it again. Kave was fixing code. Retrying. And then I finally was able to quickly, so one day after Herbert sent a message, I sent a reply. Here, Herbert. I found one bit flip in row 2147 at this position. And then I also added this to the email. And here it was. So that's cool, right? So we were at March 26. I worked on the project for, well, not 10 days or so, maybe 20. And we were flipping bits on mobile devices. Never been reported before, super cool. But yeah, so we were root, and we had to install a custom kernel to get this all to work. That's not really enough for publication. So we wanted to do something more. First thing we wanted to do next is flip bits from Userspace, so from a normal application. And this is when things really went downhill. As I said, flipping bits are useless from the kernel module. So let's see what happened then. First thing I did was figure out the row size. So the matrix that I showed earlier, if you know exactly the size of one of these rows, then you can figure out when exactly you are doing double-sided Rowhammer. So I figured it out, made some fixes and updates. I ran more tests with a better version, and I found more bit flips, also on my own phone, Moto G1. We bought a new phone, an ARMv8 device, because ARMv8 has a flush instruction that you can actually use from Userspace. So we figured, well, maybe that will work. So I wrote code to test that. We tried to hammer using multiple cores to see if we could find even more bit flips. We played with memory fences, a lot of work. We played with ARM performance counters, and I got a parking ticket. Here it is. Anyway, we didn't really find a way to flip bits that easily from Userspace. So next is side channels. So I wanted to understand really what was going on when reading from memory and how the caches work on ARM, and are they that different than what we see on Intel. So I wrote some code, completely useless, but it shows you the average time per read for two read operations on different addresses. And what this shows you, do we have it here? Yeah. It shows you the cache line sizes. And then this tells you that on the phone I was testing this, the level 1 cache would have cache lines of 64 bytes. The level 2 cache would have cache lines of 128 bytes, which is different a little bit than what we see on Intel. But yeah, I found that super cool. I did another plot. Average time per read when reading a number of contiguous cache lines. So what is this here? Well, it shows you the size of the level 1 cache, which is on this phone 16 kilobyte. And then here, average time per read when reading from is the same, but it's reading more. And then we found that, oh wow, the level 2 cache is 2 megabyte on this phone. Super useless, because you can just go to Wikipedia and you will find the same. So basically what we did here was side channels everywhere. Spent quite some time on getting this to work, but never used it in paper. Okay, April 11, update from Kruegel. Ben is also looking at flushing the cache. Maybe you guys should work together. But his goal was making money. So he was doing this on iPhone and trying to get a bug bounty out of it. But he had an idea of using a Gasflush system call that might actually work. Yes, I also want to make some cache. So about Gasflush system call. So you can type this on your Ubuntu box man page for Gasflush. It's a system call that will flush the contents of the instruction and or data cache. Flush the content of the indicated cache for the user addresses in this range that you provide. Okay, cool. So the idea now is to use this system call, Gasflush system call from Userspace to flush the CPU caches. However, we know that jumping into the kernel, so doing context switches, is very expensive. And flushing the CPU cache after every read will be very slow. But then the observation was, what if we flush after multiple reads? Maybe that will work. So basically what we're going to do now is pointer chasing. So with DRAM on top and with the CPU cache in the corner, we're going to start reading from row 1, the top row, at the first offset. This will get cached in the CPU. Then we're going to read from row 3, so doing the Rowhammer trick. We'll store it in the CPU. Will get stored in the CPU cache. Then we will read from row 1 again, but now not at offset 0, but at offset 64, which is 1 cache line away, and this will also be stored in the CPU cache. We'll continue doing this until we reach the end of the row, and then we're going to call this system call Gasflush, which will clear the cache, and then we jump back to the beginning of the loop, and we do it all over again. And if you do this, then you only have to pay for the overhead of jumping into the kernel for every n accesses. So depending on how many cache lines you can read, you only have to pay the overhead for jumping in the kernel fewer times. So, but does this work, right? So I implemented this, and to make it to make it a proper proof of concept, I started with my own system call implementation of Gasflush. And I was flipping bits, so that's good. But then I moved to using the Gasflush system call of the Android Linux installation. I was no longer flipping bits. So I had to read the menu. So I went and read the menu. And then here, there was also on the man page that this cache, that's one of the arguments for the system call, can be one of the following. And if it's decache, then we will write back to memory and invalidate the affected valid cache lines. So but what does this mean, right? So invalidating a cache line, which is different than flushing. Maybe we should try the iCache, flushing the instruction cache. Can we use that? Okay. So now what we did was flipping bits by executing code, because the iCache stands for instruction cache and dcache stands for data cache. So we have two caches, the CPU, the dcache on the right, and the instruction cache on the left. And now we're going to write instructions into the aggressor rows to trigger bit flips in a row between. So the first instruction in the first row will be jump ahead 6 items. It basically will jump to the next row. There will be an instruction, I'll jump back 5. And then we will jump forward again and jump back. And there, at the end, we will do a cache flush, and then we will jump back all the way to the beginning. And basically what we're doing here is executing instructions and then flushing these instructions from the instruction cache, so it will be gone, and try to flip bits by executing code. And it worked, right? Super cool. So we were using, again, our own system call implementation for Gasflush, and we were flipping bits by executing code. I was really impressed by this. So you can do things like Rowhammer-oriented programming if you have the right gadgets. But then I switched to using the Android Gasflush system call, and it didn't work again. So then the hypothesis was maybe this implementation of Gasflush for Android is really bloated. Maybe it's maybe there's too much overhead introduced by it. So I read the manual again. I also looked at the Linux code at dinner. And then if you ever looked at the ARM manual, you will see tables like this. And then this instruction here, the MCR P15 instruction, will send a command to Coprocessor 15. R4 is the MVA, the virtual address to flush, or the address to flush. And then these values map into this table. And then you can use this table to figure out what you're actually doing. So I traced Gasflush, the implementation. I figured out where this was, how this was implemented in Linux. It was pretty deep. You have to go down and down further. It gets uglier on the way. But then finally, I found the implementation in this file listed over there. So here are the 2 MCR instructions, MCR P15 instructions. Okay, so this green line, the green row, was the instruction that I was using, and I was flipping bits with this instruction. As soon as I was switching to the others, it didn't work anymore. And then if you look at the difference, so they're sort of similar. The only thing that's different is POU and POC. And then I already saw this before, POU, I looked it up, point of unification, okay. But this time I really had to figure out what it was doing. And POC was point of coherence. So what is the difference between unification and coherence? So yeah, you read the manual. Again, on the beach. And then you find a definition that says that the point of coherence is typically the main external system memory. On the other hand, point of unification is a unified level 2 cache. For example, in a system with Harvard level 1 caches. So, illustrated with some figures, point of unification versus point of coherency. If you have one of the phones I was looking at, Nexus 5, has 4 cores with their own level 1 caches. And then there was a level 2 cache on the CPU that was shared between the 2 cores. And then below that, there's the DRAM. So if you're calling one of the MCR instructions that invalidates to point of unification, what's happening is that it's flushing the CPU core, so the level 1 core, and then it's moving the data back from the level 2 core, from the level 2 cache into the level 1 cache of the CPU. So it will never actually reach DRAM. While on the other hand, if I was using the invalidate until POC, point of coherence, it would clear the CPU cache from the core, and then also the level 2 cache. And then it will move back the data from DRAM into the core. So this was working, and this is why our approach of using the system call, the Gasflush system call, didn't work. Nevertheless, it was cool. So the conclusion was that, yeah, attack research is hard and risky. I was saying, yeah, it's not very easy. You will learn a lot in the process, and you ask yourself the very philosophical questions. And then actually this April, so I also sometimes play capture the flag games or hacking competition games. April was like 1 month of a CTF. And then it was really, yeah, we really had some very good conversations on Hangout. How could they design this? Yeah. And we became desperate. Yeah, let's stop. Yeah, it's too crazy. We're not going to do this. So I sent an email to the rest of the people involved, and bad news. We tried everything, because pointer chasing, execution, even writing. So we were also able to flip bits by writing into memory, but only if we use our own implementation. So what's left? Cache eviction sets or DMA, direct memory. I'm going to look at the first, but it didn't look good either. And then actually the conclusion was, so this was closed less than a month before the deadline, that we were going to write a paper about why Johnny cannot flip bits on ARM. So he can flip bits, but they're useless. So then Martina replied, and then she said, yeah, I looked into DMA a little bit on Android, and what could be interesting is Ion. And Ion is this memory subsystem in Android, and it provides large physically contiguous buffers used by cameras and stuff like that you can allocate from Userspace. And apparently, these buffers have their own caching policies. Can you see if this device is available on your Android device, phone? Yeah, it was there. And it was readable by everybody. So normal users can simply open this and communicate with it. And indeed, it sounds interesting. So a little bit about DMA. Going back to this first step of flipping through memory templating. Finding a way to bypass CPU cache. So this picture is incomplete because sometimes CPU caches are undesired. You don't want them actually there. For example, if you have a dedicated device that is also communicating with the DRAM, for example, GPU, then the CPU can do other tasks in parallel, while the GPU is operating on the memory. And in this example, you don't want data to get stored in the CPU cache, because then the CPU might be looking at different data than the GPU is. So there's need for every operating system to have some sort of DMA, direct memory access. Then about the second issue, the second challenge for an attacker, if we recall, selecting the aggressor rows, so figuring out the mapping between virtual and physical. Now, with DMA, you will see that sometimes these devices that are working with memory, so the GPU or an audio device, they're very stupid, and they cannot really understand virtual to physical mappings. So then this means that shared memory between the CPU and a device must be contiguous. And then what you get is basically DMA memory that behaves very much like huge pages. So you allocate with the graphical allocator in this case, and you end up with contiguous memory allocations. So I found this out, or actually I looked at one of the few resources on this, and then I told Kabe, yeah, this is it. This is where we can find bit flips. Ion. What is this? No. If you find flips in Ion, then yeah, that's actually not a good thing, because it was April 29. I was there in Santa Barbara with my girlfriend and my daughter. Of course, we had to see the region, so we were going to LA. Also, there was security and privacy coming up, so we had to travel to Oakland, San Francisco. I have to make a presentation for security and privacy. Also, we wanted to go to Yosemite Park, one of the national parks in the area. We also needed to do whale watching, everything. So, so if we find bit flips with this, that means we also have to do the entire attack afterwards, right? And we only had, well, less than a month, so better not work. Well, of course it works. I was flipping bits. Kabe was happy. Is this with the eviction strategy? No, it's with Ion DMA. So, of course, I was at Santa Barbara at the group there, and they have a professor. I didn't name him here, so he's very famous. He's very good. And I told him the news, right? So yeah, we can finally flip bits. And then when he said, "Okay, great. So you found the right library. Congratulations." Yeah, okay, it was a bit of a downer, but yeah, really, what can we do so far, right? At this point, early May, so we can flip bits on ARM. Yeah, maybe we can analyze a bunch of phones to see how many of these phones are actually vulnerable. I can say something about that. And then perhaps we can port one of the existing Rowhammer exploits to mobile. But then again, yeah, that's, for research-wise, it's not really a lot, right? It's merely a port, and we need a better exploit. So the goal from here on was to get some kind of deterministic exploitation. So the Google Project Zero exploit is non-deterministic. It sometimes works, it sometimes doesn't work. And we don't have memory deduplication. So we don't have a way to get some interesting data stored at a region that is vulnerable to Rowhammer. So the guys at VU scheduled a meeting when I was asleep. And then there was this very smart guy, Herbert Bos. Kave started talking to me and saying that I was screwed because they came up with a possible attack using Ion, but Herbert Bos was involved. And you can imagine how complicated it got. And if you know Herbert Bos, then you know that this is true, because as soon as he's involved, I'm usually out of the way. So I told Kave that I'm out. If Eric is in, then I'm out. It's over for me, right? I can't compete. This guy is super smart. Kave was bringing it slightly different. he was saying, finally, you do cool enough stuff for Eric Bosman to help you out, to show up. Nah, man, no. I'm out. I'm going to get a corona. So I got a corona. And then, so who is Eric Bosman? He's the guy who did SIG return-oriented programming, and he also did deduplication as Machina, also at Security and Privacy. And he won awards, so he did 2 very big projects that both won awards. So he's really a smart guy. Anyway, after the VU meeting was over, I got an email from Gave with the subject, your next few weeks. So it's 20 days before the deadline. This is what he sent me. It's a picture of the whiteboard. And yeah, I can't work with this, right? So if you get this, you lost. So we had a Skype talk, and then after the Skype, it was much better because I wrote it down myself. But at least after the Skype call, it was clear that what we had to do, landing sensitive data. The threat model that we're going to assume was a recent Android operating system without any kind of memory deduplication. And then we have an unprivileged app that wants to get the root access. Now, to get there, to get to the root access, basically what we want this app to do is to get access, read-write access to anywhere in memory. Because once we can read and write anywhere in memory, we can find our own administrative data structures for our own process, and then we can override our user ID and get root access. So the goal is read-write access. The approach that was basically laid out in those figures was to land a page table at a location that is vulnerable for Rowhammer. And then we're going to flip a bit in a page table entry. So about page table, who knows here what a page table is? Okay, good. They map virtual addresses to physical addresses. I think I have to hurry up a little bit. So you have a buffer, and then the virtual addresses and the physical addresses. These are stored in the table, virtual to physical. So where are they stored, the page tables? Of course, they're stored in memory. So they could be stored there, between your allocations. What happens if we flip a bit there? Well, we can modify the mappings. For example, if we flip this physical address here, the binary representation, this one will flip, and basically we're updating the mapping to now point to the page table itself. And once we have access to page tables, we can read, write anywhere in memory, because we can modify entries of the page table, and we can add new ones. The question remains, however, how do we get this page table stored exactly at the location between our own buffers? So for this, we came up with Flip Feng Shui. And I have to rush a little bit. So basically, this is your memory, and you have some allocations from apps running already in the background. What we do is we're going to allocate large chunks of memory. Allocating. Then we're going to look for bit flips. It will find one at some point over there. Okay. Then we're going to allocate rows of memory. So we're going to allocate this and this. Next, we're going to release the large chunk that has a vulnerable bit flip. And then we're going to exhaust the rows again. And now the bit flip is in one of the rows that we've allocated, which we can release, give it back to the system, and then we can also release larger chunks. And now we can allocate pages. And if we're going to allocate pages, the operating system will make sure that the smaller holes are filled first before going to the larger holes. So this means that we can allocate more pages until we hit the page that is vulnerable to Rowhammer. And then we can do this trick with mmap to generate a new page table, and we can map it exactly at the location that we want it to be. Okay, so one more figure, I think. One more photo. Because I was talking with Cristiano, who was also involved in this, and I couldn't get the last piece, the last thing right, so there was one missing piece. So what do you mean? And then it was this, yeah, how do we know that we actually allocated enough pages until we are there? So I explained him my personal issues for a minute, and then he said, yeah, super cool. Another thing, are you around tomorrow? I can drive to Santa Barbara, and we can look at this. So he drove to Santa Barbara, because actually he was around, and then we had one afternoon of brainstorming session where he was explaining how things should be done and how it's going to work. So we ended up fixing the problem that we was running into. And then I got to move on to evaluation. So they have a bunch of phones there in Santa Barbara, connected them all in a very professional setup to do our evaluation. And we found, so this is a snippet of the result that we have in the paper. We found bit clips on 18 out of 27 devices. And then sometimes you have one Nexus 5 with no bit clips, and then you have another Nexus 5, so same model, with close to 1 million bit clips. Not every bit clip is exploitable. Sometimes we find the first bit clip that we can actually exploit after 1 second, but then sometimes it will take 50 minutes before we find the first bit clip that is usable. In general, we found that once we have this first bit clip, the rest of the exploit will take 22 seconds. So the largest part of the attack is spent in finding bit clips. So I had to wrap it up. To do the evaluation, we had to visit the national park. And to search for a site settle to fix this last step. There was security and privacy, there was paper writing, and then was submitting. And afterwards, in June and July, we're not done, of course, because we only had the steps. We knew it was going to work, but we didn't have the end-to-end exploit. We didn't have a video. And we also had to contact Google. So quickly about that. Exploit writing looked like this. Looking at screens like this, finding the bit slip, and then there it is. Disclosure with Google was also fun. So we contacted them on July 25. And why is this date important? It's important because it was 91 days before the paper would get published, CCS, so paper got in. And 91 days is enough for Google. At least Google Project Zero gives Google 90 days to fix their issues. So we were way on time. And then at some point we had a video call with the Google guys, and then they were asking, yeah, maybe can you publish in another venue later this year, so we have more time to fix it. But the paper was accepted at CCS, which is a pretty decent venue, I would say. So we said no. And then they said, yeah, what if we throw some more money at you? We also said no. And then the best part was, maybe, then if you cannot submit to another venue, can you obfuscate some part of the paper so that it's harder for other people to replicate your research? No, we also didn't do that. We were rewarded 4K bug bounty. And then in November there was a first patch. They patched it more afterwards, so they continued working on a better solution. But to conclude, now what? So the conclusion of this talk, besides all the funny stories, is that Rowhammer exploitation now is really widespread because Flip Shui showed we can do it on the cloud. People showed that we can do it in the browser. And we can also break your mobile device with this. Bitflips have been reported on all different types of DDR modules. And we can do, with this work, we can do reliable exploitation without relying on custom operating system features like deduplication. Another conclusion is that software was never written, never designed to deal with these kind of hardware issues. And we see that proposed defenses so far, they're still in early stages or easily bypassed. And even hardware mitigation, so there are some proposals there. They're still optional, and also they don't always seem to work as expected. You cannot fix Rowhammer. So if you have a device that is vulnerable, you cannot open it up and then get the DRAM out, fix it, solve it, and get it back into your device. So it's unfixable. And we think more research is necessary to figure out what else is possible from an attacker side, but also on the defense side. So that's it. You can find more details about the Drammer, and we have a Drammer app at our project page. Some part of the code is open sourced, and you can follow me on Twitter. Yeah, that's it. Thank you.